Welcome to the DOE, the Genesis mission, Transforming Science and Energy Funding Opportunity Walkthrough. FOA number DE, FOA-0003612. This presentation covers 106 focus areas across the Genesis mission challenge areas. Each focus area represents a specific research opportunity where AI can accelerate scientific discovery and energy innovation. Challenge Area 1. Reenvisioning Advanced Manufacturing and Industrial Productivity. This challenge area has 6 focus areas for fiscal year 2026. This focus area asks for teams to develop agentic AI, integrated with digital twins, to revolutionize chemical manufacturing. The goal is to create self-driving and self-adaptive chemical laboratories capable of discovering and deploying new chemical processes and catalysts. This unique approach aims to accelerate the production of large-scale critical chemical building blocks using domestic resources. Researchers with expertise in autonomous AI, chemical engineering, and advanced robotics for laboratory automation would be a strong fit. Here, DOE is looking for teams that can develop AI models to integrate diverse datasets from multimodal synthesis, characterization, and fabrication. The core objective is to leverage high-throughput simulations and predictive theory to accelerate the transition from novel material discovery to rapid scale-up, integration, and deployment. This focus area is unique in its emphasis on bridging the gap between fundamental materials research and industrial application. Ideal applicants will have expertise in AI, materials science, and data-driven manufacturing. This focus area asks for the development of AI-driven digital twins specifically for first-of-a-kind energy technologies, with a strong emphasis on fusion energy systems. The goal is to connect physics, materials behavior, manufacturing processes, and systems operations data to enable the design and fabrication of high-performance components. This is unique due to its focus on extreme energy environments. Ideal applicants will have a background in AI, digital twins, advanced manufacturing, and a deep understanding of fusion energy challenges. This focus area seeks to expand the use of physics-informed AI methods, digital twins, and advanced controls to optimize existing processes across various industrial sectors. The goal is to enable real-time process control and dispatch of energy resources, particularly within energy-intensive industries like chemicals and steel. What makes this unique is the emphasis on generalizable, scalable solutions with proof of concept. Ideal applicants will have strong backgrounds in industrial AI, process optimization, and experience with diverse manufacturing environments. This focus area aims to leverage AI-driven smart and secure manufacturing technologies to enable digital transformations across industrial facilities. It specifically calls for developing agentic AI for system-level optimization and reasoning, training digital twins to model a real-time, hyper-realistic smart factory floor, including equipment and human states. This unique emphasis on hyper-realism and human integration distinguishes it. Ideal applicants will have expertise in agentic AI, digital twins, smart manufacturing, and advanced simulation for complex industrial environments. This focus area seeks to leverage AI-enabled digital twins to optimize advanced synthesis and roll-to-roll processes for energy materials and solid electrolyte-based electrochemical devices, such as fuel cells. The goal is to integrate multi-physics models and real-time data for comprehensive monitoring and closed-loop control, accelerating end-to-end digital transformation. This is unique due to its specific application to energy material manufacturing. Ideal applicants are primarily DOE/NNSA national laboratories with expertise in AI, digital twins, and advanced materials processing. Challenge Area 2. Scaling the Biotechnology Revolution. This challenge area has 5 focus areas for fiscal year 2026. This focus area asks for research to determine fundamental principles connecting protein structure and function. DOE is seeking AI-driven approaches to accelerate biosystems design applications and understand complex biological systems. Teams should propose innovative AI models for biomolecular design, integrating omics technologies and advanced simulations. This is crucial for developing predictive models and foundational principles in biotechnology, making it ideal for researchers in computational biology and AI. This focus area seeks to link genomic, biomolecular, metabolic, and environmental factors to predict phenotypic outcomes in microbes and plants. DOE is looking for AI-driven approaches to understand complex biological networks and improve predictive models. The goal is to reduce data requirements and enable more efficient model training for predicting phenotypes in environmental contexts. This is crucial for advancing bioenergy and biomanufacturing, making it suitable for teams with expertise in systems biology, AI, and ecological modeling. This focus area aims to develop a complete understanding of how genetic and environmental factors influence microbial communities. DOE is seeking AI-driven models to predict microbiome gene expression and interactions, enabling the engineering of microbiomes for various applications. This research is critical for advancing biomanufacturing, resource extraction, and plant health. Teams with expertise in microbial ecology, AI, and computational modeling of complex biological systems would be a strong fit. Here, DOE is looking for teams that can utilize predictive principles to design, control, and optimize traits in plants and microorganisms. This focus area emphasizes accelerating the design-build-test-learn (DBTL) cycle through innovative AI approaches. The goal is to enhance the prediction of engineering outcomes and accelerate the discovery of broadly compatible genome engineering tools. Researchers with expertise in synthetic biology, AI, and high-throughput experimentation would be well-suited. This focus area seeks to develop AI and digital twin models to streamline R&D in biological reaction engineering, bioreactor design, and process scale-up. The goal is to predict and address complexities for cost-effective production of biofuels, biochemicals, and bioproducts. This is crucial for accelerating biomanufacturing processes from lab to industrial scale. Teams with expertise in process engineering, AI, digital twins, and bioprocess optimization are encouraged to apply. Challenge Area 3. Securing America's critical mineral supply. This challenge area has 7 focus areas for fiscal year 2026. This focus area asks for innovative AI approaches to expand America's critical mineral resource base. The core challenge is to de-risk projects by integrating geophysical and chemical data with AI for process prediction and cost estimation. Teams should leverage existing national lab datasets. This is crucial for securing domestic supply chains and would suit researchers in geophysics, data science, and economic modeling with expertise in AI applications for resource management. Here, DOE is looking for teams that can develop and deploy AI-enabled automated discovery platforms. The goal is to accelerate material discovery, manufacturing, and qualification through integrated closed-loop systems. This approach aims to reduce the demand for critical minerals by finding alternatives or more efficient uses. Researchers with expertise in materials science, AI, automation, and experimental design, particularly those focused on sustainable materials, would be a strong fit. This focus area seeks proposals to implement Athena, an AI toolkit for holistic economic network analysis. The objective is to synthesize critical mineral supply and demand data, enabling robust scenario analysis of policy interventions and geopolitical disruptions. This is vital for understanding and securing critical material supply chains. Ideal applicants would possess expertise in economic modeling, AI, data analytics, and international relations, with a strong background in critical minerals markets. This focus area aims to develop AI-enhanced technologies for the entire critical mineral supply chain, from domestic extraction and midstream processing to refining and recycling. The goal is to establish complete domestic supply chain capabilities, leveraging existing national lab data. This is crucial for reducing reliance on foreign sources. Researchers with expertise in AI, chemical engineering, materials processing, and sustainable resource management, particularly those familiar with DOE/NSA data, are encouraged to apply. This focus area addresses the challenge of locating and extracting critical minerals from diverse geological sources, including subsurface and unconventional sources like mine tailings. It seeks AI models that integrate geophysical, advanced sensing, and soil system insights to predict and characterize CMMs. The research should also develop AI capabilities for recovery from various environmental matrices. This is crucial for expanding domestic resource access and requires expertise in AI, geology, geophysics, environmental science, and remote sensing. This focus area seeks AI models to identify chemical drivers for significantly improving the separation of critical minerals from complex, heterogeneous mixtures. The unique aspect is integrating knowledge across multiple length and time scales, from quantum to macroscopic properties, including molecular interactions and energy exchanges. This is vital for efficient processing and purification. Ideal applicants would have expertise in AI, chemistry, materials science, and chemical engineering, particularly those focused on advanced separation techniques. This focus area explores biological pathways for critical mineral recovery, separations, and refinement, leveraging AI-guided discovery. The challenge is to understand and engineer how microbes, proteins, and plants interact with minerals at a molecular level to enhance CMM extraction and improve efficiency. This unique biohybrid approach offers novel opportunities for recovering CMMs from dilute sources. Researchers in AI, microbiology, biochemistry, plant science, and environmental engineering, particularly those with expertise in biomining or bioremediation, would be a good fit. Challenge Area 4. Delivering nuclear energy that is faster, safer, cheaper. This challenge area has 8 focus areas for fiscal year 2026. This focus area addresses the challenge of accelerating nuclear power plant design and licensing. DOE is seeking AI-driven solutions to create automated processes for rapid design, autonomous monitoring and control of operations, and swift deployment of advanced nuclear technologies. This is crucial for enhancing safety and efficiency in the nuclear sector. Teams with expertise in AI, automation, and nuclear engineering would be a good fit. This focus area targets improving the safety and operational performance of nuclear power plants. DOE is looking for proposals to develop AI digital twin systems capable of interpreting real-time operational data, detecting anomalies, and recommending preemptive actions. This unique approach leverages AI for predictive maintenance and enhanced operational reliability. Researchers with strong backgrounds in AI, digital twins, sensor data analysis, and nuclear plant operations are encouraged to apply. This focus area addresses the challenges in nuclear manufacturing and construction. DOE seeks AI-driven solutions to support site selection, born certified manufacturing, construction, supply chain reliability, and modular production methods. The goal is to leverage AI, predictive analytics, and automation for efficient delivery of nuclear components. This is crucial for reducing costs and accelerating deployment. Teams with expertise in AI, manufacturing, supply chain management, and nuclear engineering are ideal candidates. This focus area aims to significantly shorten nuclear material research and qualification timeframes. DOE is looking for AI-driven pipelines for modeling, characterization, evaluation, and qualification, integrating vast historical irradiation data. This unique approach leverages AI to accelerate the R&D cycle, critical for reactor deployment and operation. Researchers with strong backgrounds in AI, materials science, nuclear engineering, and data analytics, particularly with large data sets, would be well suited to apply. This focus area addresses the critical need to secure the domestic fuel supply by accelerating fuel cycle facility design and licensing. DOE seeks automated AI-driven processes for rapid design, efficient licensing, and swift deployment of advanced fuel cycle technologies. This is vital for enhancing national energy security and reducing costs. Teams with expertise in AI, automation, nuclear fuel cycle engineering, and regulatory processes are encouraged to submit proposals. This focus area aims to accelerate waste disposition site characterization. DOE is looking for proposals that leverage AI modeling for the collation, evaluation, and analysis of large, diverse datasets from sources like USGS and geologic surveys. This unique approach uses AI to enhance the understanding of subsurface conditions, crucial for designing safe and effective waste repositories. Researchers with expertise in AI, geological sciences, data analytics, and environmental engineering are ideal candidates. This focus area addresses the critical challenge of designing repositories for nuclear waste. DOE seeks AI-driven proposals for the concept design of licensable mined geologic repositories for used nuclear fuel, reprocessed fuel, and high-level waste. This unique application of AI aims to optimize repository design, ensuring long-term safety and compliance. Teams with expertise in AI, geological engineering, nuclear waste management, and repository design are strongly encouraged to apply. This focus area aims to unlock the value of historical nuclear industry data. DOE is seeking proposals for the development, utilization, or adoption of AI and ML tools to efficiently review, classify, and release legacy documents. This unique application of AI or ML can significantly shorten technology development cycles and reduce costs by making historical information accessible. Researchers with expertise in AI, machine learning, natural language processing, and information management, particularly with large document corpuses, would be a good fit. Challenge Area 5. Accelerating delivery of fusion energy. This challenge area has 7 focus areas for fiscal year 2026. This focus area asks for research to centralize material characterization data and train AI models to support the engineering and qualification of materials for fusion power plants. The goal is to develop materials that can withstand extreme conditions like high neutron flux and thermal loads. Teams with expertise in materials science, data management, and AI or ML for predictive modeling would be a good fit, contributing to the foundational science needed for fusion energy. This focus area seeks applications addressing challenges in plasma-facing materials, specifically those interacting directly with plasma under extreme conditions. It emphasizes deploying digital twins of exposure facilities to characterize material properties and support qualification. Researchers with expertise in materials science, plasma material interactions, and digital twin development for extreme environments are encouraged to apply. The goal is to advance materials crucial for the longevity and performance of fusion reactors. Here, DOE is looking for teams that can apply AI and machine learning to real-time plasma control systems. The goal is to create, sustain, and optimize fusion-relevant plasma scenarios, ultimately achieving sustained energy output. This area is crucial for advancing fusion confinement approaches. Applicants should have expertise in plasma physics, control systems, and advanced AI or ML techniques, particularly for autonomous methods in dynamic environments. This focus area addresses the critical challenge of managing tritium in fusion reactors. It seeks AI models to track, forecast, and optimize tritium separation, storage, and inventory, aiming for fuel self-sufficiency. This is vital for the practical operation of fusion power plants. Teams with expertise in nuclear engineering, chemical processing, and AI or ML for complex system optimization are encouraged to apply to advance these essential fuel cycle technologies. This focus area aims to advance tritium breeding blanket concepts, which are essential for fusion fuel self-sufficiency. It seeks proposals to build standardized databases for critical material properties and deploy multi-physics AI models. This research will help understand and predict blanket performance under fusion conditions. Teams with expertise in materials science, nuclear engineering, and multi-physics modeling with AI integration are well suited to contribute to this vital aspect of fusion energy development. This focus area seeks to establish a centralized, standards-based data repository for fusion plant engineering and system integration. It aims to connect AI, HPC, and digital twin capabilities across fusion facilities to advance balance of plant technologies, including power conversion and control systems. This is crucial for developing integrated, efficient fusion power plants. Teams with expertise in large-scale data management, AI or ML, HPC, and systems engineering for complex industrial facilities are ideal candidates. This focus area seeks to leverage AI and machine learning to revolutionize plasma science and technology. The goal is to enhance control, analyze large data sets, automate detection and prediction, and accelerate experimental throughput and discovery. This is crucial for rapidly advancing our understanding and capabilities in fusion. Researchers with strong backgrounds in plasma physics, data science, and AI or ML for scientific discovery and real-time control are ideal applicants. Challenge Area 6, Transforming Nuclear Restoration and Revitalization. This challenge area has 3 focus areas for fiscal year 2026. This focus area asks for proposals to implement the EM-AI R&D roadmap. It addresses the challenge of coordinating AI investments across environmental management sites. Teams should focus on converting historical data into standardized, multimodal formats suitable for AI applications. This involves developing integrated knowledge management systems to accelerate environmental management and decision-making. Researchers with expertise in data standardization, AI for complex datasets, and knowledge management for environmental applications will be a good fit. Here, DOE seeks proposals to develop a scale-bridging AI foundation model. The core challenge is predicting complex behaviors across different scales, from lab to full-scale systems. This involves leveraging EM operational data, advanced simulation toolkits, and Genesis mission supercomputing resources. The goal is to create a predictive framework that accelerates critical treatment milestones and compresses deployment timelines. This area is ideal for teams with expertise in multimodal AI, large-scale data integration, and high-performance computing for complex physical systems. This focus area targets the optimization of waste treatment processes using AI. The goal is to improve throughput and achieve completion milestones at key EM sites like SRS and Hanford. Proposals should focus on implementing AI for real-time dynamic process controls, leveraging diverse data sources, including sensor data and historical records. This is crucial for efficient decontamination, decommissioning, and nuclear material separation. Ideal applicants will have expertise in AI for industrial process control, data fusion, and complex system optimization. Challenge Area 7, Discovering Quantum Algorithms with AI. This challenge area has 5 focus areas for fiscal year 2026. This focus area asks for research using AI to develop application-aware error correction for quantum systems. The goal is to co-design algorithms and hardware that can efficiently identify and correct errors specifically impacting scientific results. This is crucial for achieving reliable quantum computation. Teams with expertise in AI, quantum error correction, and hardware-software co-design would be well suited to address this challenge. Here, DOE is looking for teams that can develop computational tools for fault-tolerant quantum science. This involves using AI and formal verification to create novel, reduced complexity, quantum algorithmic primitives and compilation tools. The ultimate goal is to deliver scientific quantum advantage. Researchers with expertise in quantum algorithms, formal methods, and AI-driven compilation for fault-tolerant systems are encouraged to apply. This focus area asks for research into hybrid quantum classical optimization algorithms, specifically using agentic AI workflows in quantum chemistry and material sciences. The goal is to move beyond iterative parameter space searches, leveraging AI-driven surrogate models to accelerate quantum time evolution and many-body simulations. This is ideal for teams combining expertise in quantum chemistry, material science, and advanced AI optimization techniques. This focus area seeks the development of quantum algorithms, potentially leveraging AI, specifically tailored for nonlinear plasma physics problems. The primary objective is to apply these algorithms to facilitate the configuration development and optimization of fusion devices. This is a critical area for advancing fusion energy research. Researchers with expertise in quantum algorithms, AI for scientific discovery, and plasma physics, particularly those focused on fusion applications, are encouraged to apply. This focus area seeks to leverage AI to determine quantum computation advantage in nuclear and hadronic systems, particularly those described by lattice quantum chromodynamics. It aims to enable solutions using quantum algorithms that demand AI to tackle fundamental challenges like chiral symmetry breaking and confinement. This is ideal for researchers with expertise in nuclear and hadronic physics, quantum algorithms, and AI for complex physics simulations. Challenge Area 8. Realizing Quantum Systems for Discovery. This challenge area has 4 focus areas for fiscal year 2026. This focus area asks for AI frameworks to understand the causal relationships impacting quantum system performance. The goal is to improve designs and refine processes for synthesizing and fabricating quantum devices. Researchers should propose AI-driven solutions to accelerate the development and manufacturing of next-generation quantum technologies. Teams with expertise in AI, quantum physics, material science, and engineering would be a strong fit. Here, DOE is looking for teams that can implement AI-based methods to dramatically improve real-time control of practical quantum systems. This includes automating and optimizing critical processes like calibration, noise mitigation, and error correction. The goal is to achieve accurate, practical, and scalable quantum control for a wide range of users. This area is ideal for researchers with expertise in AI, control theory, and experimental quantum systems. This focus area seeks proposals to integrate AI into multi-qubit quantum sensing applications. The goal is to achieve extreme sensitivity in both laboratory and field environments. AI should enhance and optimize the design, fabrication, and operation of sensors leveraging quantum properties of various materials. Researchers with expertise in AI, quantum sensing, materials science, and device engineering are encouraged to apply to advance quantum measurement capabilities. This focus area asks for leveraging AI to address critical challenges in quantum computing and networking. Key objectives include mitigating qubit decoherence, developing effective quantum error correction codes, and enhancing control over quantum processing units. The ultimate goal is to ensure the scalability of quantum processors and network systems. This is an excellent opportunity for researchers in AI, quantum information science, and computer architecture. Challenge Area 9. Recentering Microelectronics in America. This challenge area has 10 focus areas for fiscal year 2026. This focus area asks for AI-enabled nano and microfabrication techniques to accelerate angstrom-scale manufacturing. The scientific challenge is pushing beyond current limits like Moore's law and EUV lithography to create advanced node logic. DOE is looking for teams that can develop approaches enabling greater design flexibility. This is crucial for advancing microelectronics at the fundamental scale, making it a good fit for researchers in materials science, AI, and advanced manufacturing. Here, DOE is looking for teams that can leverage AI to accelerate research into novel materials for non-von Neumann computing devices. The opportunity lies in exploring emerging organic and inorganic candidates, including 2D materials and those with quantum effects, to overcome efficiency and performance bottlenecks. This focus area is unique in its pursuit of radically different computational paradigms, making it ideal for researchers in materials discovery, quantum computing, and AI-driven design. This focus area seeks AI-based methodologies for designing next-generation computing architectures. The scientific challenge involves optimizing complex hardware/software interactions and performing multi-scale systems modeling. AI research is sought to model, prototype, and integrate hardware and software development, identifying highly efficient, application-specific architectures. This is important for advancing computing capabilities and is a strong fit for experts in AI, computer architecture, and systems engineering. This focus area calls for AI-driven co-design to revolutionize 3D non-volatile compute and memory technology. The opportunity is to integrate these emerging technologies and materials into electronic, optoelectronic, or photonic computing applications. AI is crucial for accelerating research, development, and prototyping, particularly for back-end-of-line integration. This area is important for advancing memory and processing capabilities, making it suitable for researchers in AI, materials science, and advanced computing hardware. This focus area seeks to leverage AI for physics-based circuit design, simulation, and emulation. The scientific challenge is linking material properties and operating conditions to device performance and defect evolution, which are computationally intense. AI is sought to accelerate these processes and enable non-intuitive optimization and greater design flexibility, including for electronic design automation. This is important for fundamental advances in microelectronics, fitting researchers in AI, physics, and circuit design. Here, DOE is looking for teams that can integrate AI into the design and validation of robust microelectronics for harsh environments. The challenge is ensuring efficient operation and high data volume processing where replacement or service is impossible. AI research is sought to create devices that can withstand extreme conditions. This is crucial for applications in space, nuclear, or other inaccessible settings, making it a good fit for experts in AI, materials engineering, and extreme environment electronics. This focus area seeks to leverage AI to revolutionize plasma-based processes for microelectronics manufacturing. The scientific challenge is pushing the boundaries of feature size and geometry. AI research is sought to optimize the design, control, and discovery of optimal and repeatable plasma synthesis conditions. This is important for advancing manufacturing capabilities and creating next-generation microelectronics, making it ideal for researchers in AI, plasma physics, and advanced manufacturing processes. This focus area calls for deploying AI-driven design and manufacturing approaches for advanced power electronics and communication networks. The opportunity is to develop technologies like wide bandgap power electronics and advanced wireless communication, such as 6G. AI is crucial for optimizing the design and production of these critical components. This is important for modernizing energy infrastructure and communication systems, making it a good fit for researchers in AI, electrical engineering, and telecommunications. This focus area addresses the bottlenecks, preventing the practical realization of low-temperature electronics for sensors and computation. The opportunity lies in developing cryogenic CMOS and superconducting logic for efficient, high-speed, and low-cost computing, particularly for edge computing and AI accelerators. AI research is sought to overcome challenges in design, density, scaling, fabrication, and integration. This is crucial for next-generation computing, fitting researchers in cryogenics, quantum computing, and AI hardware. This focus area aims to transform neuromorphic computing by addressing connectivity, communication, and system hardware integration challenges. The scientific challenge is integrating neuromorphic hardware at scale for scientific computing. AI research is sought to leverage multi-scale connectivity and connectome data to design high-bandwidth, massively parallel connectivity for emerging neuromorphic processing units. This is important for scaling brain-inspired computing, making it ideal for researchers in AI, neuroscience, and computer architecture. Challenge Area 10, Securing U.S. Leadership in Data Centers. This challenge area has two focus areas for fiscal year 2026. This focus area asks for the development and demonstration of AI models to manage data center load flexibility. The goal is to orchestrate smart, grid-aware techniques like workload management and cooling modulation, enabling data centers to respond to real-time grid conditions. This will help reduce peak demands and stabilize grid fluctuations. Researchers with expertise in AI, energy systems, and data center operations are encouraged to apply. Here, DOE is looking for teams that can apply AI-based tools and approaches to advanced data center thermal management technologies. The objective is to enable peak performance and efficient operation for current and future AI and computing chipsets, addressing challenges at the chip, rack, and facility levels. This is crucial for sustaining high-powered computing. Ideal applicants will have strong backgrounds in AI, thermal engineering, and high-performance computing. Challenge Area 11, Achieving AI-Driven Autonomous Laboratories. This challenge area has 5 focus areas for fiscal year 2026. This focus area asks for research into advanced robotics and embodied AI systems for dynamic laboratory environments. The goal is to develop computational and algorithmic capabilities for robots to navigate, perform tasks, and manage experimental workflows, ultimately reducing scientific discovery costs. Teams with expertise in robotics, AI, and high-performance computing are encouraged to apply, aiming to create adaptive and efficient discovery platforms. Here, DOE is looking for teams that can develop AI tools and technologies for research network operations, or AIOps. The objective is to enhance reliability and resilience in autonomous laboratory settings, supporting AI-driven science. This involves AI-enabled data curation, predictive analysis, and proactive network mitigations. Applicants with domain science expertise and a focus on high-performance research networks are a good fit. This focus area seeks to extend AI beyond data processing to achieve autonomous generation of scientific knowledge. The key is AI-enabled identification of phenomena or correlations in high-throughput data that challenge existing models, leading to new testable hypotheses. This aims to optimize research direction and accelerate discovery, making it ideal for teams focused on fundamental energy science and AI-driven hypothesis generation. This focus area calls for AI-driven robotics to perform remote handling and diagnostics in fusion power plants. The goal is to manage tasks like handling irradiated materials and maintaining equipment, with feedback control and edge AI accelerating data processing and stability analysis. This research is crucial for maintaining stable reactor conditions and minimizing experimental damage, making it suitable for teams with expertise in robotics, AI, and fusion energy systems. This focus area seeks to accelerate the design and prototyping of neuromorphic computing circuits for robotic embodied AI. It emphasizes understanding brain-inspired computational components and translating biological primitives into functional circuits. The aim is to develop novel neuromorphic systems that can learn and adapt, leading to high-performing computational systems. Teams with expertise in neuroscience, AI, robotics, and advanced computing hardware are well-suited. Challenge Area 12. Designing materials with predictable functionality. This challenge area has 7 focus areas for fiscal year 2026. This focus area asks for teams to develop physics-aware AI frameworks and foundation models. The goal is to orchestrate high-throughput computation and simulations, enabling a fundamental understanding of functional, quantum, and emergent material properties. This research aims to predict and realize physical properties currently inaccessible, crucial for advancing technologies like lossless power transmission and quantum devices. Ideal applicants will have expertise in AI, physics, and material science, seeking to push the boundaries of material discovery. Here, DOE is looking for teams that can develop interpretable AI models and agentic experimental workflows. The core challenge is to discover, understand, and manipulate the complex interactions governing structural materials, especially under stress and extreme environments. This focus area aims to enable controlled design of mechanical behavior, which is critical for advanced energy systems. Researchers with expertise in AI, material science, and high-performance computing, particularly those focused on structural integrity, would be well-suited. This focus area seeks proposals to establish AI frameworks that integrate atomic and molecular modeling across scales. The objective is to bridge biological and chemical data, enabling a design-to-order paradigm for new biomolecular materials. These materials are specifically intended for hierarchical structures suited to extreme environments, addressing critical needs in various applications. Researchers with expertise in AI, computational biology, chemistry, and materials science, particularly those focused on novel material design, are encouraged to apply. This focus area asks for the deployment of AI-enabled digital twins for heat and plasma exposure facilities. The primary goal is to support the characterization, manufacturing, and qualification of materials that interact directly with fusion energy plasmas. These materials must withstand extreme temperatures, neutron fluxes, and environmental stresses. This unique challenge requires expertise in AI, fusion energy, material science, and advanced simulation to accelerate the development of robust plasma-facing components. Here, DOE is looking for teams to establish AI-driven targetry by design to accelerate breakthroughs in isotope production, enrichment, and chemical separation technologies. The overarching goal is to expand the portfolio of domestically produced isotopes and secure a reliable U.S. supply chain for critical sectors like energy, computing, and medicine. This area is vital for national security. Ideal applicants will combine expertise in AI, nuclear chemistry, and material science, focusing on innovative isotope production methods. This focus area asks for the deployment of automated discovery platforms to accelerate the identification and design of novel manufacturable energy materials. The goal is to develop closed-loop autonomous systems that integrate hypothesis generation, experimental validation, and manufacturing processes through AI-driven frameworks. This will compress multi-year qualification processes, addressing critical needs in various material types. Researchers with expertise in AI, materials science, automation, and advanced manufacturing are strongly encouraged to apply. This focus area solicits projects using AI to accelerate the search for platinum group metal, PGM, free oxygen reduction catalysts for electrochemical energy conversion devices. The challenge lies in the intricate and time-consuming synthesis routes of current materials. This topic seeks to improve repeatability for existing catalysts and develop new, higher-performance PGM-free alternatives through AI-guided materials synthesis and performance prediction. Ideal applicants will have expertise in AI, electrochemistry, and material science, focusing on sustainable catalyst development. Challenge Area 13. Enhancing particle accelerators for discovery. This challenge area has two focus areas for fiscal year 2026. This focus area asks for teams that can develop and deploy AI systems to enhance the operation of particle accelerators. The goal is to provide real-time operational advice, automate control functions, and improve beam stability, ultimately reducing tuning time and predicting equipment failures. A key approach involves creating AI-driven digital twins for sophisticated simulation and design. This is crucial for optimizing both existing and new accelerator facilities, making them more efficient and cost-effective. Here, DOE is looking for teams that can integrate digital twins to achieve real-time control of nuclear fusion systems. The challenge involves leveraging massive experimental data and high-fidelity simulations to monitor stability and provide crucial feedback control. This focus area is unique in its application to critical fusion technologies like tokamaks, stellarators, and inertial fusion devices. Researchers with expertise in AI, control systems, and fusion energy science would be well-suited to apply, aiming to accelerate the development of practical fusion power. Challenge Area 14. Unifying physics from quarks to the cosmos. This challenge area has three focus areas for fiscal year 2026. This focus area asks for teams to develop and curate essential data to train foundation models for particle interactions and cosmology. The scientific challenge is to accelerate breakthroughs in understanding the universe by integrating diverse data from experiments like the electron-ion collider and cosmic observations. Successful applicants will leverage AI to synthesize multimodal, petabyte-scale datasets, addressing scalability and interpretation challenges. This is ideal for researchers with expertise in large-scale data management, AI model development, and high-energy or nuclear physics. Here, DOE is looking for teams that can develop AI methods to significantly accelerate and enhance the Dune Science program. The core challenge is to reduce the time for publishing neutrino oscillation measurements and improve sensitivity to neutrinos from core collapse supernovae. This focus area seeks innovative AI solutions to streamline data analysis and enable new flagship measurements. Ideal applicants will have strong expertise in AI or ML, high-energy physics, and experience with large-scale experimental data, particularly within neutrino physics. This focus area seeks partnerships between domain experts, data scientists, and industry to develop AI methods for expedited discovery from high-complexity, petabyte-scale datasets. The challenge is to extract robust scientific insights, connect data with theoretical parameters for uncertainty-aware reasoning, and automate big data analysis. This will improve understanding of the universe and particle interactions, addressing issues like the slowdown in lattice QCD. Ideal applicants will bring expertise in AI or ML, high-performance computing, and particle or nuclear physics, with a focus on deployable solutions. Challenge Area 15. Predicting U.S. water for energy. This challenge area has three focus areas for fiscal year 2026. This focus area asks for teams that can develop and apply AI capabilities to understand complex, nonlinear multi-scale interactions in atmospheric microphysics and turbulence. The goal is to improve predictions of precipitation formation, phase, and intensity. Researchers should propose AI-driven analysis techniques to extract new insights from atmospheric field datasets. This is crucial for advancing climate and weather modeling. A good fit would be AI experts with strong backgrounds in atmospheric science. Here, DOE is looking for teams that can enhance the predictive understanding of surface and groundwater, vital for energy production and flood protection. The core objective is to leverage advanced AI techniques to develop a coupled surface groundwater model. This model should improve hydrologic process understanding and water availability predictions, especially for regional energy needs. Ideal applicants would combine expertise in AI, hydrology, and Earth system modeling to address critical water resource challenges. This focus area addresses the need for skillful regional water predictions over seasonal to multi-year timescales. It seeks proposals leveraging generative and explainable AI to accelerate and refine the DOE Energy Exascale Earth System Model, E3SM, and complementary data-driven models. The goal is to improve process components of coupled models and understand nonlinear variability. This is critical for informing energy system planning. Researchers with expertise in AI, climate modeling, and Earth system science are encouraged to apply. Challenge Area 16. Scaling the grid to power the American economy. This challenge area has 3 focus areas for fiscal year 2026. This focus area asks for proposals leveraging AI to enhance grid modeling and analysis. The goal is to develop more comprehensive and robust tools for grid planners, helping them understand the impacts of various interventions on grid behavior. Key interests include creating foundational power system models with self-improvement capabilities and AI-driven model copilot tools for rapid scenario analysis. This is ideal for teams with expertise in AI, power systems, and advanced modeling, aiming to provide optimal insights for grid operations and long-term infrastructure planning. Here, DOE is looking for teams that can use AI to fundamentally enhance grid operational efficiency, stability, and responsiveness. Proposals should focus on developing and deploying AI-augmented tools for measuring grid dynamics, identifying anomalies, and providing advanced data analytics and decision support for operators. Projects should leverage real-time grid data to offer optimized recommendations for grid control, resource dispatch, and risk mitigation. This area is crucial for improving grid reliability and cost-effectiveness, seeking innovators in AI and power systems operations. This focus area asks for research into uncertainty quantification within grid planning and operational models. The core challenge is to investigate the sources of uncertainty, including multi-sector inputs, and explore how AI can either expand or reduce these uncertainties. Projects might examine external forcings on the power grid or the impact of differential privacy in federated learning models on outcome uncertainty. This area is critical for improving the reliability and trustworthiness of grid models, making it suitable for researchers with expertise in AI, statistics, and complex systems modeling. Challenge Area 17. Unleashing subsurface strategic energy assets. This challenge area has 3 focus areas for fiscal year 2026. This focus area asks for AI-driven approaches to improve understanding and prediction of subsurface processes. It seeks to integrate vast data sets, including molecular scale interactions, with mechanistic and process-based predictive models. This is crucial for advancing hydrological, geochemical, and ecological modeling. Researchers with expertise in AI, subsurface science, and multi-scale data integration would be a strong fit, particularly those focused on developing robust predictive models for complex subsurface environments. Here, DOE is looking for teams that can leverage AI to advance geophysical understanding of subsurface fractures. The focus is on characterizing fractures in the upper crust, particularly those relevant to enhanced geothermal systems and hydrocarbon recovery. This area is unique in its specific focus on fracture evolution and its direct application to critical energy resources. Researchers with strong backgrounds in geophysics, AI, and energy resource management, especially in geothermal or hydrocarbon domains, are encouraged to apply. This focus area seeks proposals using multivariate and multi-scale data, HPC, and AI to understand subsurface fracture interactions. The goal is to measure and evaluate natural and induced fractures before, during, and after stimulation, enabling rapid analysis and real-time decision-making. This will improve recovery and cost-effectiveness for unconventional hydrocarbon and geothermal energy. Ideal applicants will have expertise in AI, geophysics, mechanical engineering, and real-time data analytics for energy resource development. Challenge Area 18. HPC code curation, translation, and development for accelerated scientific. This challenge area has 7 focus areas for fiscal year 2026. This focus area asks for AI systems that can analyze and optimize existing complex scientific codes. The goal is to automatically identify performance bottlenecks and generate optimized code, especially for GPU and other heterogeneous architectures on leadership-class computing facilities. Teams with expertise in AI, high-performance computing, and compiler technologies will be a good fit to enhance code efficiency and portability. This focus area seeks AI solutions that can automate the entire scientific code generation process. The challenge is to translate high-level problem descriptions into governing equations, intelligently select appropriate numerical algorithms, and ultimately produce high-quality, documented code for novel scientific problems. Researchers with expertise in AI, scientific computing, and automated reasoning are encouraged to apply to advance the frontier of scientific software development. This focus area targets the development of neurosymbolic AI agents for scientific code development. The core idea is to merge the strengths of neural networks with symbolic reasoning to enhance code generation, algorithm selection, and performance prediction for scientific and engineering codes. This unique approach aims to overcome limitations of purely data-driven or rule-based systems, making it ideal for teams specializing in hybrid AI and scientific computing. This focus area seeks innovative AI approaches for predicting and improving code performance. The goal is to develop graph-based predictors and surrogate models that can map code to hardware features, accurately predict performance, and diagnose bottlenecks. A key aspect is incorporating continuous learning from performance feedback to enable iterative improvement. This is ideal for teams specializing in performance modeling, machine learning, and compiler design for high-performance computing. Here, DOE is looking for teams that can ensure the trustworthiness of AI tools used in scientific software. The focus is on developing AI solutions that offer numerical correctness guarantees, ensure reproducibility, track provenance, and provide interpretable performance diagnostics. Crucially, these tools must incorporate uncertainty quantification to support risk-aware decision-making. This area is well-suited for researchers focused on robust and verifiable AI for critical scientific applications. This focus area addresses the challenge of building intelligent code models by integrating multimodal data. The goal is to combine diverse data types, including DOE code bases, compiler representations, performance logs, and hardware counters, to train comprehensive foundation models. This approach aims to create a holistic understanding of scientific software behavior. Teams with expertise in large-scale data integration, machine learning, and high-performance computing are well-suited for this opportunity. This focus area emphasizes collaborative partnerships to advance HPC coding, specifically for manufacturing and materials engineering. The objective is to leverage AI for automating various aspects of the software lifecycle, including code generation from problem formulation, optimization, testing, and workflow orchestration. This unique focus on industrial applications makes it ideal for interdisciplinary teams combining expertise in AI, HPC, and materials science or manufacturing processes. Challenge Area 19, AI for Scientific Reasoning. This challenge area has 3 focus areas for fiscal year 2026. This focus area asks for teams to develop foundation models with provably enhanced capabilities for complex mathematical operations and symbolic manipulations. The goal is to create trustworthy AI crucial for deriving and verifying scientific theories. This is unique due to its emphasis on provable reliability in AI for fundamental scientific reasoning. Researchers with expertise in formal methods, mathematical logic, and AI for scientific discovery would be a strong fit. Here, DOE is looking for teams that can build AI systems capable of synthesizing information from diverse sources, including scientific literature, experimental datasets, and simulation outputs. The core objective is to identify gaps in current knowledge and formulate novel, testable hypotheses. This focus area is crucial for accelerating scientific discovery by automating the initial stages of research. Ideal applicants will have strong backgrounds in multimodal AI, knowledge representation, and scientific reasoning. This focus area asks for the development of strong-based large language models designed for flexible integration with other specialized foundation models and tools. The goal is to enable complex, cross-domain reasoning across scientific areas like genomics, material science, or grid modeling. This is unique in its emphasis on modularity and composability for broader scientific application. Researchers with expertise in LLM architecture, model integration, and multi-domain scientific AI would be well-suited to apply. Challenge Area 20, Cybersecurity for AI-driven science workflows. This challenge area has 3 focus areas for fiscal year 2026. This focus area asks for research into making AI models robust against adversarial attacks, specifically within science-dedicated workflows. The goal is to develop AI-powered tools that can autonomously probe these models for vulnerabilities, benchmark their resilience, and generate methods to harden them. This is crucial for ensuring the trustworthiness of AI in scientific discovery. Teams with strong backgrounds in AI security, adversarial machine learning, and scientific computing would be well-suited to apply. Here, DOE is looking for teams that can address the critical challenge of data trustworthiness in AI workflows. This focus area seeks scalable frameworks and automated tools to verify data provenance and detect malicious compromise, such as data poisoning or manipulation, in large-scale scientific datasets. Ensuring the integrity of data used for AI model training and inference is paramount for reliable scientific outcomes. Ideal applicants will have strong backgrounds in data security, provenance, and large-scale scientific data management. This focus area asks for the design and demonstration of AI-based systems capable of real-time attack detection and mitigation for science-dedicated AI models. The core challenge is to identify when a model is under attack during training or inference and deploy immediate strategies to limit impact and preserve workflow integrity. This is vital for maintaining trust in dynamic scientific AI applications. Researchers with expertise in real-time AI security, anomaly detection, and automated response systems for machine learning are encouraged to apply. Challenge Area 21. Artificial Intelligence in Fluid Flow for Energy Components and Technologies. This challenge area has 10 focus areas for fiscal year 2026. Focus Area A. Physics-Informed AI for Complex Flow Modeling, ISO, BER, ASCR, FES. Develops AI models that integrate fundamental physical laws and domain knowledge to accurately represent and predict complex fluid phenomena, e.g., wall-bounded turbulence, bluff body flows, particle F. Focus Area B. AI-driven design and control for performance and durability, ISO, ASCR. Develops AI methods, particularly generative AI and reinforcement learning, to remove the bottleneck of fluid flow modeling, rapidly explore vast design spaces, and identify optimal configurations. And Focus Area B. Program Goals, Objectives, and Priorities. The Office of Sciences SC mission is to deliver scientific discoveries and major scientific tools to transform our understanding of nature and advance the energy, economic, and national security of. Focus Area C. Data-driven operational intelligence and system resilience. Integrates AI-enabled fluid flow models with real-time sensor data of energy systems to enable improved state estimation, anomaly detection, predictive maintenance, and adaptive control. Through this, Focus Area C. Award contribution to goals and objectives. Awards resulting from this RFA are intended to speed up science and transform energy through the use of AI. Focus Area D. Performance goals. Phase 1 awards will be expected to demonstrate progress towards demonstrating AI advantage in your selected focus area through a go/no-go evaluation at 6 months. Focus Area E. Program unallowable costs. Applications will be informed of cost principles and standards that comply with 2 CFAR Section 930.210 after selection. Focus Area F. Citations to statute and regulations. The programmatic authorizing statutes and governing regulations are U.S. Department of Energy Organization Act, codified as amended at 42 U.S.C. Section 7256, 2020. Act of July 4, 2025, Pub L, number 119-21. Focus Area G. Program History. You can learn about SC's history at https://science.ost.gov/about/history. You can read about our achievements at https://science.ost.gov/science-features/science-highlights. You can find information. Focus Area H. Other information. Anticipated award size. The award size will depend on the number of meritorious applications and the availability of appropriated funds. Period of performance. DOE anticipates making Phase 1 awards with